I also want you to look at the abbreviations. So let's go ahead and talk about our warm-up today. The warm-up is focused on these energy types, and anytime you're writing it down in this pie chart or in an LOL chart, you want to use the abbreviation because it's super long to write out gravitational potential energy. But as I stated, there's two types of abbreviations for these. One, for example, KE, oh, that's not it. That's a promotion for chemistry. So KE, the capital abbreviation, is what we use in physics, but a lot of our worksheets use the AP Physics abbreviation, which would be E subscript K. So I want you to be familiar with both because I'm not rewriting all these worksheets. They're pretty intuitive. So it's pretty easy to guess and to figure out what each symbol represents, but if you have to write it down, use one of these abbreviations and I'll know what you're talking about. Okay, let's start with the first one. In this first scenario, you've got a pie chart. You guys all know what pie charts are. It represents ratios or percentages of, in this case, different types of energy. And we have three because we've got three parts of a ball drop that I want you to analyze the energy for. The first scenario is the ball at the very top of its motion. It's not moving. Remember when we learned about motion maps? Anytime there's a dot, that means that the velocity is 0. And then each vector represents the speed. So this shows a small speed and then a larger speed. Now, I wrote this note here. The ball is very close to the ground. It hasn't quite hit the ground because if it did hit the ground, the velocity would be 0. But we know that the velocity is at its maximum speed because when you drop a ball, it starts at 0 meters per second and it increases every second by 9.8 meters per second squared, right? So I want you to think of anything that is just above the ground at maximum speed to be basically 0 height. If there's 0 height, there's 0 gravitational potential energy. Because remember, gravitational potential energy represents a height above the ground. It has potential for falling. So anytime you hear the words just before it hits the ground or just after it hits the ground, those key words, I want you to tell me that the height is basically 0 and that there's no gravitational potential energy. Even though there's a teeny tiny bit, when we start doing calculations, it's much easier to say, oh, that's so small, it's not significant, instead of having to calculate a gravitational potential energy with a height of maybe 0.01 meters. It's insignificant, okay? Just like when we talk about air resistance, it's so small, it's insignificant. So keywords, anytime it says just before or just after, say that the gravitational potential energy or the height is basically 0. The other thing I want to talk about is scenario number 2. And I feel like my students broke my little wind-up toys. I couldn't find a bunny. But the bunny, if you notice, has velocity vectors under it also. You don't truly know what's happening within a wind-up toy, but you can guess, right? You can intuitively figure out what's going on in here. So as the bunny is fully wound up, notice how it has some motion because the velocity vector shows that it's moving. So this is the initial state. But as it goes, it gets slower and slower until it fully stops. So this is your analysis of the wind-up toy. When it is moving, with high velocity, what energy types are present within the wind-up toy, when it is slowing down, and then when it is stopped. So first you have to decide what energy types there are, right? The pie chart is going to represent a symbol of how much of each energy type there is. So I'm not going to give you the answer. Actually, I'm going to give you the most wrong answer. But let's say in the first scenario, I say, oh, there's a lot of chemical energy here. So I'm going to say it's all chemical, but maybe there's going to be a sliver of thermal. And then in the next scenario, I'm going to say, oh, this is all kinetic energy. So the way you're doing it is you're going to look at each part, each step. What energy type is there? Is there more than one? And if there's more than one, how does it split up in that specific scenario? Does that make sense? We haven't done this before, so I'm not expecting you to get it right. I just want to see what you think, and the best place to start is to look at this sheet. You've got 5 different energy types. There's more than this, but we're going to focus on just these 5. And then figure out what energy is present here. What energy is present here? What energy is present here? What ratio of the different energies are there in each step? Okay? Do your best. So let's get into our ball drop. We've got gravitational potential energy because it is high above the ground. There's no kinetic because this dot means it's not moving. And then in the second scenario, we've got a velocity vector. So there's definitely motion, which means kinetic energy, and there's gravitational potential energy because it's still above the ground. Now, for 3, it's just before hitting the ground. Remember, just before hitting the ground means that the height is basically 0, and it is at its maximum speed. When you drop the ball, it starts at 0, and it increases speed, and it reaches its max, just as it hits the ground. I had a good question. So this one will be all kinetic energy. I had a student ask, would there be elastic energy if it's a rubber ball and it has bounce? It would if it said that the ball hits the ground. And usually what you would see in the diagram is instead of a perfect sphere, you'll see that the ball has flattened. And that would be elastic potential energy. But in this case, it hasn't hit the ground yet, which means there's no compression and there's no elastic potential energy. So this one would be all kinetic. Any questions on number 1? Okay, so for question number 2, this one was intended to be a little bit more critical thinking. You start with high elastic potential energy because it's completely wound up, but you also have motion. So some students might have done a different ratio, maybe more elastic, less kinetic, but this is fine for me. Half kinetic, half elastic looks good. And then the second scenario, I want to see that the kinetic energy decreases because look at this arrow. Your velocity goes from a high velocity to a shorter velocity. So this kinetic energy, if it starts off as half, it should be maybe a quarter. The other type of energy there is elastic. And elastic, because you're unwinding this wind-up toy, the elastic potential energy is going to decrease because anytime you have an elastic, the more you stretch, the more elastic potential energy is built up. But as you unwind, the elastic potential energy gets smaller and smaller and smaller. So that's what happens with a wind-up toy. This is the problem. I have this extra space here. There has to be energy there because based on conservation of energy, we cannot lose energy and we cannot gain energy. So what would that possibly be? That's it. If you look at this wind-up toy and you look at the interactions it has with its surroundings, there's a lot of back and forth friction between the wind-up toy's feet and the ground. I have another one that bounces. Thermal energy can be created out of collisions also. So I'm just going to show you because they're fun. But even if it was a bounce, this type of wind-up toy would also have thermal energy because that constant collision creates heat. So this has thermal. And then finally, we have a bunny that is completely at rest, which we can assume the elastic is completely undone. There's no elastic potential energy, and there's all, this student put internal. You're going to see this in your concept builder. This is the same thing as thermal. It just means that the thermal energy is within the system or the bunny and the ground. So I am, is that part of this worksheet?
Yeah, it says
EINT, good. So E internal would be something that you're going to see in your concept builder tonight. So that's perfect. Are there any questions? This one was the hard one because a lot of students just think, is there nothing? There's never nothing. The energy has to go somewhere. It has to transfer somewhere. Just like your money in your bank account, it's got to go someplace. And in this case, it goes into thermal energy. Any questions on this? Okay, so I'm going to tell you a little story. So my son, he's just kind of this wild child, and he is incredibly passionate. He has this set of blocks. Actually, I thought it was so appropriate because we are going to be working with blocks today, but he has this set of blocks. There's 28 of them, and every night we have to count all of his blocks to make sure all 28 blocks are there before he can go to bed and sleep soundly. So one day we were counting his blocks and we only found 27. He freaked out. We searched the entire house and eventually found it under the rug. We have 28 blocks. He went to sleep. He was happy. The next day, we were counting his blocks at the end of the night, and I found 30 blocks. And I had no idea how he could have gotten from 28 to 30. And then I realized his dad had taken him to the park. He's obsessed with blocks. I talked to my husband. He said he found these blocks. He brought them home. That's where the 30 came from. I took the 30. I got rid of them. We're back to 28. The next day, he had been playing in mud. It was raining. He had been playing in mud all day. He was super dirty. He was in the tub. It took a long time for him to get clean. And as he was in the tub, I was counting his blocks, and I only found 26. So I'm searching the house. I looked under the rug. I checked everywhere it could possibly be, and it wasn't anywhere. I go back into the bathroom, and as I'm cleaning him, I realize, okay, this tub is more full than I had originally put it because there's this like permanent ring. There's no way of scrubbing it out. And so I always fill the tub to the same height every night. And it was higher than it originally was. So I asked my son, are your blocks in there? He said no, with this little sly smirk on his face. And he was adamant that I not search the tub. So the physics nerdy me, I started doing my calculations. I thought, well, the height of the tub is about 6 inches. Right now, it's a little bit higher than that. So I take the height difference of the two. I throw one of his 26 blocks into the tub and realize it moves up 1/4 inch. And with my calculations, I realized he's got to have 2 blocks in there. It adds up perfectly. So I got 26, I can see them, and I have 2 that I have calculated have got to be in there. Sure enough, they were. The next day, I'm searching, I'm counting the blocks. He's missing one. We've got 27. I'm searching the house, under the rug, in the tub, everywhere it could possibly be, and it's nowhere. So I finally find it outside his window. He had thrown it outside. It was right under the bush, right outside his window. I pull it back in. We've got 28 blocks. So this is a perfect description of energy. Energy is your 28 blocks. If you count them up total, they're always going to stay the same. Now, it might seem like you're missing some, but it's still there. It's just in a different energy type. And this is why my block description is a perfect scenario for transfer of energy. There's always going to be 28, and it's always going to be one place or another, but if you look really carefully, you're going to find it. It's in thermal, or you're going to find it. It's in chemical energy, but it's going to be there. Now, the reason why I did all those calculations is because we have an equation, or we have equations in our physics helper to calculate gravitational potential energy. It's mgh, mass, gravity times height. We've got kinetic energy, 1/2 mv squared. We've got an equation for elastic potential energy, 1/2 kx squared. But we don't have an equation for thermal, and we don't have an equation for chemical, but we can always do a calculation with our mechanical energy types, the ones that we have equations for, and determine how much chemical and how much thermal energy is left based on the difference, just like what I did with the calculation of the height difference in the water. So that is my little energy symbolism story with my crazy son. Let's go ahead and talk about these blocks. So we've got these energy blocks, and I'm going to use tape for this one because I feel like it worked out better with tape for my last class. So let's look at the first problem. We've got a Jeep, and in this Jeep, actually, this. So we've got a Jeep going up the ramp. It starts at the bottom. So let's just say the Jeep is right here. This is worksheet 1. So pull out worksheet 1. And then it ends at the top. It says it's moving at constant speed. So I'm going to put my velocity vectors to be about the same length. And we're going to do an LOL chart with this. When you do this worksheet with your groups, you're going to take a whiteboard. You're going to draw out your LOL chart. So it doesn't stand for laugh out loud. It just looks like an LOL. So what you're going to do is you're going to take the initial scenario. The Jeep is at the bottom of the ramp, and it is moving at constant velocity up the ramp. My initial scenario, when the Jeep is at the bottom, what energy type would I have here? What do you think? What energy would I have? Danny.
I feel like both kinetic energy and gravitational potential is probably mostly gravitational.
So there's going to be gravitational eventually, but to start, it's going to be at the bottom of the ramp first. So you're right, we're going to have kinetic. So it doesn't matter how many blocks you put, but I'm going to throw in 2 Ks for kinetic energy. You can put 1, and then when it reaches the top of the ramp, what energy type would I have then? Any thoughts? Anya? And thermal? Well, if it's not sliding, if the wheels aren't sliding, we can assume that there's no thermal energy. But you're right, it would have gravitational for sure, and it would have kinetic. Now, more specifically, how much kinetic energy should I put in this LOL, in the second LOL tape?
Just one, so it's like even on both sides.
So I do have 2 here, and we do want it to be even. So yes, make sure that it's even. I have 2 kinetic energy because remember it says it's at constant speed. So 2 kinetic, 1 gravitational, and what else, Spencer? What do I need?
I was gonna say you could have thermal energy because of the engine running that produces heat.
You could have thermal energy. Let's not get too complex about it. Let's just say, consider thermal energy if there's friction or if there is a collision. And in this case, we're just gonna say any other energy, thermal energy from heat from the engine or the battery or anything else like that would be negligible. But here's the problem. I've got 2 blocks here. I've got 3 blocks here. So this car is moving up the ramp and it's got to get energy from somewhere to get to the top of that ramp. Mika. So this one would be a battery car. It's basically the Jeeps that we used when we did the constant velocity lab in class. So what we would actually electric energy is something we're going to cover when we get into electricity. I think unit 7.
If it's the battery, then
It's chemical. The battery, a person, or a motor, we're going to call that chemical energy. The energy from the battery is what allows this car to move up to a higher gravitational position. So we forgot to do one thing though. We forgot to include the system. Anytime you do an LOL chart, at least for this worksheet, you're going to create the system yourself. So what I'm going to tell you is in order to create the system, we need to think about all the things that are interacting with this Jeep, just like what we did with the force body diagram. What are the things that are interacting with my Jeep here? I want new volunteers. What is this Jeep touching? Any long-range forces? What would I want to put in my system? First thing, I want to put the Jeep in my system. What's touching the Jeep? The ground. Or let's say the rim. Anything else? What about my long-range forces? Gravity. When you write objects in your system, you want to write objects rather than an idea. So what creates gravity would be Earth. And then I'm going to add one thing here. And I'm going to do it 2 ways. I'm going to say the Jeep includes the battery. So the battery is part of the system. That means the chemical energy is going to be part of your LOL chart. When you draw your LOL charts, it's a bar graph. So when you draw kinetic energy, you just draw it like this with 2 boxes. Or chemical energy, you draw it like this. But when you play around with these blocks, I want you to make sure that as you're playing around with them, you can see that chemical is transferring to gravitational. So that's the idea behind using blocks here. Also, it's just like quite a hands-on thing to do. Here.
is gravitational on our
You know what? I think we forgot to put that in. Just add it. Sorry about that. Here, you have all the energy types. Just add it to the end. EG, and then include your gravity there. I forgot to mention that. I realized that the first one was missing that part. Okay. Here's something a little bit tricky. Your system can be defined a different way. Let's say we didn't include the battery as part of the system. Let's say the Jeep without the battery. So the battery is outside my system now. When I told you the story about my son bringing home blocks from the playground, that is an outside source putting energy into my system. So the way you would draw that, I'm going to just show you, because this is how it's going to look in your homework. It's going to be chemical from an outside source, that's the battery, and it's going into my system. The way you would count it is you've got 2, 3, and it has to equal 3 here. So we're still having equal parts of energy to start and equal to end. So I want to make sure that this is clear, that however you define your system is going to change what your LOL diagram looks like. With the battery, you're going to put chemical energy in your bar graph. Without the battery as part of your system, you're going to call energy an outside source. It's going to be blocks coming in from some other kid, some other household, and you're bringing it into your house or your system. You call it, you make it look something like this. Question? No. So here's the thing about energy. As long as they're equal, you could have 4, 5, 6, you could have 1 on each side as long as it's balanced. So you're not graded on the amount of blocks, you're just graded on what type of blocks there are. And as long as this total equals this total, you're good.
So
Question?
the ratio.
As long as you have, if you have 10 here, as long as it equals out to 10 here, totally fine. All right, let's do, so we kind of did the first one together. We're gonna go into, actually, let me have you get into your groups. Again, everyone might have a slightly different answer. It doesn't mean it's wrong. These questions, and I hate the way they're worded because it's a little, it's kind of open for interpretation, but just try to read it really, really carefully. So, for example, question 3, question 4 give you an initial and a final scenario. So when you see that, you want to think about what energy is their initial. But for question number 2, it doesn't tell you what the initial scenario is. It just says a wind-up toy is already wound up. The way I interpret it is that it is wound up and not moving. The way some of my students in first period interpreted it is that it's wound up and moving. So their answer's not wrong. It just means that they interpret it differently. And then it's released and walks across the table. So make sure that if you decide to interpret and draw your LOL chart a certain way, that you can validate it. Because we're gonna present our answers to the class. Does that make sense? In their seats, because this concept builder, I'm gonna go over a couple questions with you, but I wanna make sure that I provide you a little bit of guidance before you go home and start working on this. I don't want you to spend hours and hours and hours on this concept builder. There are a lot of little details that you might get stuck on. So I have a virtual tutorial during tutorial tomorrow. So pop into that and I can provide you with help. But your homework tonight is to correct worksheet 1, which we kind of did in class. If you watch my video, it might have slightly different answers than the ones we covered in class. But if you're not sure about the answer you got, just come and see me. And then we've got Concept Builder 5.2 for the LOL chart. Doing wizards only. Anya had a good question. They got finished early. They started working on the homework together. You're going to have this new energy type called INT. That is internal energy, which is also interpreted as thermal energy. But it's thermal energy that is inside the system. So let's go through the first 2 problems together. It's going to be something you're going to see in your homework. Okay, this defines the initial and the final state. It also defines the system for you. So for this first question, it says a barbell is at rest, no kinetic energy, and it's on the floor of the weight room. So if I don't have kinetic energy and it's on the floor, I don't have gravitational either. This final state says the barbell is 3 meters above the floor. So I have gravitational because now it's above the floor and it is lifted by the weightlifter. So when you're looking at the system, it includes the barbell and the earth. I have gravitational here. Where did this gravitational energy come from? Kaya? So it's lifted. That weightlifter gives me what type of energy? Chemical. Now, there's chemical here, but is the weightlifter part of the system? No. So if the weightlifter is not part of the system, you click in the middle of this box, you're going to see energy in. And if you click it again, you're going to see energy out. Energy in is your chemical energy. I want it to be balanced, so I'm going to say 1 energy in from the weightlifter, and it's equal to 1 gravitational. So that's your answer. The next one. I hope this is the right one. Okay. Okay, so this one's a tricky one. A roller coaster car is in motion on the crest of a large hill. It's got motion and it's on a large hill. I've got kinetic energy. I've got gravitational energy. The roller coaster car is in motion at a faster speed. Faster speed means I have more kinetic than I started off with on the crest of a second smaller hill. So it's on a hill. It's a smaller hill, which means this one has to be bigger. The system includes the roller coaster, the track, and the earth. And during the motion, the car undergoes significant bouncing and wobbling. That's put there for a reason. What does that tell me? Significant bouncing and wobbling. What energy type would that give me? Greta? Elastic? Anya? Thermal. It doesn't say that there's any rubber or any sort of like elastic substance, but it does say that there's collision. So you want to include thermal. Now there are 2 ways to include thermal. You can include it as the internal, but that's only if the 2 things that are bouncing together, you've got the cart and the track. Are they both part of the system? Yes. So I would include internal energy here. Now I want to do a scenario. Let's say the track was not part of the system. I have thermal energy in the car, but I also have thermal energy from a track that isn't part of the system, and thermal energy is always energy out. And this is for the track. You have 1 thermal energy internal from the car, because the car is part of the collision, and you have 1 thermal energy from the track, because the track is also part of the collision, but outside the system. Does that make sense? So half and half. What I would have to do next is include an extra gravitational, because if I have 1, 2, 3, 4, 5, I would need 5 here. Any out energy is going to be added to your final scenario. Any inward energy gets added to your initial scenario. So for this one, if it was exactly the way it was, I'm going to go back here. I would have internal, gravitational, 2 kinetic. I need to have 4 on this side. Because the car and track are part of the system, everything is going to be within my LOL chart. Notice I can't click an answer or to submit my answer. It's because you have to go through the in and out scenario before you can Check.